Venn diagrams are everywhere. From memes to serious applications, this way of organizing things is very popular. They usually don't go beyond 3 sets, where they look rather simple. But it's possible to go beyond, to 4, 5, 6 and even more sets, where they start to get very complex. I wanted to find a way to systematically draw these complicated diagrams. Bonus points if the resulting diagrams are aesthetically appealing. In this video I'm sharing what I learned along the way, and showing some different ways I found to build pretty diagrams. While you can technically slap some sets together in order to represent a relation between different properties, a proper Venn diagram is capable of representing any relation. That means it must have one region for every combination of being inside or outside of all sets. For example, if we look at this figure made out of 4 circles, we're missing AC and BD. That is, the region inside A and C but outside B and D, and the region inside of B and D but outside A and C. If you give it a try, you see that it's not as easy to come up with a proper diagram for 4 sets. But it's possible nevertheless. Intuitively, the reason why it becomes harder as the number of sets grows is that the number of regions grows really fast. For each set, there's a possibility of being inside or outside. For each of these choices, we will have a region in the diagram. Since this is a choice among 2 possibilities made n times, we must have 2 to the power of n regions. Suppose then that we have a diagram with n sets and we want to add another one. This new set will need to double the number of regions, and as we'll see soon, it must do that by crossing all the previous regions, splitting them in 2. The problem is that as more and more sets are added, the regions get spread out in more and more complex patterns, meaning the sets we need to get more complex. As I mentioned, one way to add a new set to an existing diagram is to use a closed curve that crosses every region, including outside of the diagram, once. The reason why this works is that it adds to every region in the diagram 2 new regions. One that is inside of the new set and another that is outside, covering all the possibilities. When I first heard of this argument, I found it was very interesting, because it connects with some ideas that could be turned into something automated. If we consider any figure that is broken into regions, with well-defined borders, like a map, we can ask ourselves how we can move from one region to another. If I add a dot to each region and connect the dots corresponding to neighboring regions, we get what we call a dual graph. If we consider the dual graph for a Venn diagram, then adding a new set that still gives me a proper diagram is equivalent to finding a path in the graph that goes through every dot once and goes back to the beginning, which is what we call a Hamiltonian cycle. The problem is that even though this helps guiding you where to add a set, if you're drawing things by hand, automating the way to handle the dual graph is pretty complicated. And even for drawing, things start to get too tight too quickly. So I decided to try something different. I looked for known diagram constructions to see if I can find any patterns, and I came across this one by Henry Smith. The idea is to look at the graphs of y of x equals 0 and yn of x equals sine of 2 to the power of n times x divided by 2 to the power of n, for n an integer and x in the interval between 0 and 2 pi. It's very interesting to see how this gets us a Venn diagram. One way is to just complete the curves like this, so these will be our sets. As we add them together one by one, we see that each new set crosses all the previous regions. But what really caught my eye is that we can look at these graphs through the lenses of polar coordinates. Suppose that we have a function f of x where f is positive. We can use this function to build a graph where x is an angle and f of x is a distance from a fixed point. So as we move along the x-axis, we trace a curve around the fixed point. Since the functions in the Smith construction repeat themselves, if we add a constant larger than 1 to make them positive, and do the same thing to then, we get closed curves, and each new curve still passes through all previous regions. So we still get Venn diagrams. This also gives us some flexibility, as changing the constant changes the look of the curves. I like this construction because it is extremely easy to build. However, I think we can still do a little better in terms of aesthetics. In particular, I'd rather we didn't have these bunches here. But we can't get rid of them, because if we move the figures a little, we start to get repeated regions. So while still technically a Venn diagram, this is more complicated than it needs to be. What's happening is that this construction relies on multiple curves crossing in the same point. Venn diagrams where this happens are called non-simple. So I then focused on how to make a construction for a simple Venn diagram. That is, one where all crossings are between just two curves. One lesson I took from the Smith construction is that we can think of each set being added as the graph of a function. And in fact, we can abstract this further, since only the vertical order of the curves matters. If, for example, this pattern appears anywhere in our graph, we know that the corresponding diagram will have a region A, AC, and ABC. Now notice what happens when we have a crossing. Before, we had A, AC, and ABC, while after we have C, AC, and ABC. In general, a simple crossing will change only one region. So I then looked for a construction for simple Venn diagrams to see if I could find a pattern in the sequence of crossings, and I came across the Edwards construction. The idea is to start with two rectangles and a circle. Then we thread a curve passing through these points. Then we thread another through here, and so on and so forth. So let's see the crossing patterns for 5 sets. Deforming the diagram a bit, we get something where we can move along an angle and check the crossings in order. Doing this leads us to this list, which at first glance looks like a mess, but I picked up a pattern. First, note that Edwards' construction works by adding one set at a time. That means that crossings involving just A and B are there since we have just 2 sets. Next, with 3 sets, the crossings AC and BC are added, then AD, BD, and CD for 4 sets, and so on. Basically, a crossing XY where Y is added later than X is created when we add Y. Watch what happens when we organize the crossings like this. The crossings seem to organize in some kind of pattern. The funny thing is that this was not a pattern I originally picked up, because I first checked the diagram with 4 sets, and I spotted this pattern instead. It fit the first 3 cases, it was easy to code, and it turns out that this pattern also creates valid Venn diagrams, which is the reason I didn't pick up on this error until I was writing this video. The final thing we need in order to draw our diagrams is to find an order for the crossings. After trying some different algorithms, I found this one that seems to always work. Try to make the next crossing in the bottom line. If that's not possible, try the lines above one by one until you find the possible crossing. If, for example, this pattern appears, the first crossing in the bottom line is the BC crossing, which we can do because B and C are next to each other. The next one would be the AC crossing, which we also can do. But after that would come the BC crossing, which now we can't do because C is on the top and B is on the bottom. So we move one line up, and the next crossing on this new line is the AB crossing, which we can do. After that we go back to the bottom line. We do now the BC crossing, followed by an AC crossing. Since we finished the bottom line, we move one line up and finish with the AB crossing. When we interpret the resulting patterns in polar coordinates, they look like this. If we move to higher numbers of sets, we end up with something where we can't really see the details. And this is because the number of crossings grows exponentially, so the size of the screen we need to grow in order to see everything. A final question I had was whether these diagrams could be made more symmetric, and researching I came across these diagrams for 5 6, and 7 sets. The ones for 5 and 7 sets are particularly interesting because it is the same figure rotated, which is not something you can build incrementally like what I did. Actually, it's not possible to find such arrangements for certain quantities of sets. Since the shapes are the same and they are arranged in a symmetrical way, they must all have the same number of crossings. So the number of crossings needs to be a multiple of the number of sets n. The regions with none and all sets are always present, while all others must come from crossings, making their number 2 to the power of n minus 2. If you test the numbers n where 2 to the power of n minus 2 is divisible by n, you find all primes, which happens because of Fermat's little theorem. There are also some exceptions known as Saurus numbers, with the smallest one being 341. So for diagrams you can feasibly draw, you need a prime number of sets. From what I could gather, diagrams for 11 and 13 sets are known, but I couldn't find a picture. And it looks like the search for a symmetrical diagram with 17 sets is still going on. Now, since we've reached current research subjects, this seems like a good spot to stop. But if you want, you can check out how to make the graph of a complex function too.